Okay, so today I want to talk to you about kinetic energy. Well, I guess to start off, it's probably better to try to define what is energy first before we get to actually doing kinetic energy, and maybe we'll get to a little bit of questions. So just want you to have a think, right? So far, from 7 to 10, what do you know about energy? So what is energy? And you probably come to realize that energy is actually quite hard to explain. Uh, Even though it is one of probably the most important concept in science or physics, it's very hard for us to give a general definition of what energy is in a few words, right? Um, but an important part about energy and why we are so interested in it in physics is because when I add up all the energy inside a system, right? So if I look at the total energy of a system, that actually remain constant or remain the same after any process. So the energy before and energy after would be the same. And so we say that energy is what we call a conserved quantity, right? So conserved meaning that it is the same before and after the process. The blue behind the gray kind of looks bad. Maybe you should do red. I'll do red. Oh, how's red? Red. Also kind of bad. But you know what? Let's just stick to black. Black is probably yes. Black is very clear. Very nice. Okay. So yeah, so energy is a conserved quantity. Okay. Now in your slide, there is this video that I put up. It tries to I really like this guy. He explains quite well, and you'll definitely see him a lot more in other lessons as well. So if you do have time, feel free to go and check out his video. Just click on the slide on Lumi, and I think it will just take you to the YouTube video. But I'll just kind of sum up what he said. So this is, yeah, I'm giving him credit for this. So energy. So how do we actually define energy? So your textbook, right? So the short, sweet definition of energy is this. This is textbook definition, right? It is the ability to cause change or to do work. So oftentimes energy is defined as the capacity to do work. But if you remember, right, how did we define work again? So we actually defined work as transfer of energy. Transfer of energy. Apologies for my handwriting. I sold my iPad, so I have to use a drawing tablet instead. But yeah, if you have a think about that, it's actually quite cyclical in nature, right? Because you go, okay, well, energy is the ability to do work, but then what is work? Work is the transfer of energy. So they're kind of defining each other in a circular format, which is not very helpful. Okay. And so, I think that can be challenging for you to try to understand. And so I'm gonna try to explain a little bit. So here's a clean whiteboard. About how all that works. Now, again, can't take credit for this. This is pretty much from the guy in the video. But if you imagined a man, right? So imagine a dude. Yeah, right. So, well, yep. Actually, I'm gonna do that. Yep. There you go. And this guy is pushing a box. Right, so I've got a box here. Now, if the guy is pushing a box, that would mean that he's applying some kind of force, right? So there is some force being applied this way. Uh, and because there's a force being applied, of course, then that would mean that the box is, accelerating. So now there's acceleration because of Newton's second law. And so therefore the velocity is changing, right? Because there's a force, therefore force that leads to acceleration. And because there's acceleration, that just means that now I have a change in velocity, right? So change in velocity. And in this case, the velocity of the box would go up. Okay. And so the motion of the box increases. And so we can then say that the kinetic energy, which is the energy of motion of the box, also increases. So, right, so by this guy applying a force on this box, right, what he's doing now is he has, increased the kinetic energy. And therefore, because he's increased the kinetic energy, he's also increased the total energy. So total energy has now gone up as well. Okay. So because of this, right, with the another, like, if you remember back to the lesson we did on work, right, by applying force on the box that is now also moving, so there's some displacement, we can say that also that this guy here, right, he has worked on the box, right? So work has been done on the box, right? Um, and so by doing this, by work being done, what he's doing, right? So what the guy is doing is he's transferring, he's giving his energy away to the box, right? So the box now has more kinetic energy. He now has some less energy, right? So work being done, that means energy is being transferred, in this case, from this guy here, right, to this box, right? So box energy increased, the guy's total energy decreased because, chemical potential turning into, like, from the food that you eat, that went down because you spent energy to push the box, right? Okay, now, so that's work, right? So that's why we say work is a transfer of energy, right? Because when work is being done, energy is transferred from one place to another place. Okay, great. Now, let us then consider the box after it's pushed. So now I have here the same box, right? It's already been pushed, and now it's moving at a constant velocity. I'm going to denote velocity in red, just so you know that it's not a force, right? So now it's going at some constant velocity. So it has energy. It is moving, right? It has some form of kinetic energy. Now let's say in the path of this box, right? So this is my ground. That's a terrible ground. Let's try that again. Here's my ground, right? There's now a ball on the ground. Okay. Now, if the ball is in the path, so let's say the ball here is stationary, right? So velocity equals 0. Okay. If the ball is in the path of the box and the box is moving this way, what is going to happen to the ball? Well, the box is, of course, going to hit the ball. It's going to then push the ball, right? And so now, instead of v equals 0, instead of being stationary, right? Once the box kind of move all the way over here, hits the ball, right? The ball will now start to move. Okay. And so, because, yeah, there's a force being applied from the box to the ball. Now, when there's a force, again, there's now acceleration. Acceleration means change in velocity. In this case, again, the velocity of the ball goes up, and that means the kinetic energy also goes up. So in this case, once again, we see that the box here, right? So this box here is doing work, right? It's doing work on the ball. And by doing work on the ball, it's transferring some of its energy, because what's going to happen to the box? The box is going to slow down, right? So this box here, right, as it hits, it's going to slow down. And so as it slows down, it's transferring some of that energy, or some of its kinetic energy, into the ball, right? And so work done means there's a transfer of energy. Okay. Now, okay, I'm just checking my notes, sorry. Yep. Right. And so the only reason why the box could work on the ball, or could do work on the ball, is only because it has energy in the first place, right? And so when it has energy, it has the capacity to do work. And so this is what we mean by, that's why we said that it's quite cyclical, right? So work is a transfer of energy. So in this case, the work is being done from the box onto the ball, right? But the only reason why this work could be done in the first place was because the box has some form of energy to begin with, right? And so that's why we say that energy is the capacity to do work, right? Because the box has energy. So I can write this down here, right? Use this one, right? So the box has energy, or more specifically, it has some kind of kinetic energy. And because it has the kinetic energy in the first place, that means that it has the capacity to do work, right? It was able to do work on the ball, right? If the box was at rest, so if the box was not moving, so let's say we have a different situation. In this case, the box was stationary, and I have the ball once again in the path, right? But both of these are stationary. Sorry, that's meant to be v equals zero. V equals zero. This one also v equals zero. Guess what? The box is at rest. The ball is at rest. There's no energy involved, and therefore there would be no capacity for the box to do work on the ball, right? Because it has no energy. And so this is what we mean by energy is the capacity to do work, and then work is the transfer of energy. So hopefully you are able to kind of understand that a little bit more. I'm sorry if I block it with my camera. I can't see it. I only have one screen, which is really sucks. So if you would like to subscribe to my channel and give me some ad revenue so I can afford a second monitor, that'd be awesome. I'm joking. But yeah, so that's a little bit about the work and energy. Okay, great. So far, this has been very useful for us to kind of conceptually understand what is work and what is energy. And I want you to keep this in mind, right? When you do questions, because you need to have a conceptual understanding in order for you to be able to solve the problem. Right. So you can see the relationship between work and energy. They're very much related, right? So work is a transfer of energy, and then energy is the ability to do work, right? Very much related. But here's the problem. This thing so far still hasn't told us what the heck is energy, right? We still don't know what is energy. But I think in order to discuss that requires quite a bit of philosophical understanding, which is beyond the scope of this course. So for now, let's just accept that energy is this kind of relative quantity, right? It's a relative quantity, and you measure energy relative to something else, right? So that's an important part. So energy, this thing here, is pretty much always going to be measured relative to something. Relative to something, right? What do I mean by that? What I mean by that is, let's say I am, I am standing at along the side of the road. A car goes by, right? So a car has some velocity. Oh, not zero. Maybe, like, let's say cars going at 10 meters per second, right? Now to me, the car is moving. It has some form of kinetic energy. However, if I myself get on a bike, I don't know how to draw a bike. I myself get on a bike. Yep, that's my bike, right? And I also travel at 10 meters per second. Now, in my frame of reference, this car here is not actually moving at 10 meters per second anymore. In my frame of reference, it's now moving at zero, right? So the car is not moving relative to me. And so with zero movement, that would mean that the kinetic energy of the car in my frame of reference is zero, right? Which is weird, but that's what I mean by energy is measured relative to something. Like, so you have to consider what is it that you're measuring energy relative to. Okay. Cool. So with that in mind, then yeah, it's a relative quantity, and you can think of energy as a possibility of an action due to difference between state of an object. So when something has energy, or when you measure energy relative between two objects, what that means is now work can be done. Right. Again, I'm kind of using a cyclical definition, but there is a possibility for something to happen because of the difference in energy. Right. For example, if I have a ground and, like, let's say I have an apple, right, and the ground, I can measure the energy of the apple relative to the ground. And the reason why this apple has energy relative to the ground is because it has a possibility of, of some action happening, right? Or some change of state, i.e., the apple has the possibility of falling down to the ground and changing the state, i.e., the height. Okay. Another example that you could probably think of is if I have, let's say, do I need another page? Okay, let's get another page. Add page. All right. So let's say if I have an isolated system, right? Now we haven't done thermodynamics yet, but for now, let's just have a think about isolated system, right? So if I have an isolated system, let's say this box here, love boxes, is, let's say, like I don't know, let's say it's 20 degrees, okay? And then this box here is, let's say, 70 degrees. Okay, so same mass, same material, two boxes, one is 20 degrees, one is 70 degrees. These boxes, let's say they are isolated, so that means that it cannot interact with the environment. So this temperature here cannot get out to the environment, right? So it's isolated, so no heat being lost here. Okay. So if I measure the energy of a two, if you remember back to, like, I don't know, year 7 or something, you would probably remember the temperature, right, is essentially the average kinetic energy of the particles in the system. Particles in an object, sure. Okay. And so what do I mean by that? Well, what that means is this block here, 20 degrees, right? If I zoom in really, really close to look at all the particles, they will be vibrating, they'll be jiggling a little bit. Okay. At 20 degrees, maybe it will kind of move around a tiny bit, like that much. Right. So kind of jiggle around, move around. 70 degrees, because the temperature is higher, what that means is the average kinetic energy is much higher. So that means the particles are vibrating and moving around a lot more. Does that mean that they all move at the same velocity or same kinetic energy? No, it's an average, right? So if you have a look at the graph, actually the graph is more like a bell curve. So you will have a bit of an extreme end. So like some with higher energy, some with lower energy, but on average, it's about a certain amount. Okay. And so that's what temperature describes. Now, because of this temperature difference, if I put the two blocks next to each other, so if I kind of now bring the two boxes together, right? So let's say this is 20 degrees, this is 70 degrees. Now there's going to be heat flow, right? Heat is going to be able to flow. So heat, if you remember back to year 8, heat is about the flow of thermal energy, whatever that means, right? Whatever thermal energy means. So essentially, the transfer of kinetic energy, or the microscopic kinetic energy between this block here, right? So as the particle can move around, it bumps at the interface with the particles in the 20 degrees box, and then some of the kinetic energy gets transferred over, and so we perceive that as heat being transferred, and so energy is being transferred, right? But that only came about because these two blocks have different amount of kinetic energy. So if you actually have a look, right, so the average kinetic energy of this thing here might be like, let's say this high. So if I draw a bar graph, maybe it's this high, right? But at 70 degrees, right, the kinetic energy might be like something like this, right? Much higher, right? And so with the difference in energy, when I put the system together, now there's a transfer, some work, I'm using this very loosely, right? Some work is being done here. Now thermodynamic works is a bit different. Again, we'll discuss that when we in the next module. But yeah, something is happening here. There's a flow on heat effect, and eventually these blocks will end up reaching equilibrium, right? So the two blocks might end up becoming like 45 degrees and then 45 degrees, right? And then once you have this, the kinetic energy is now the same. So you have slightly more, so maybe like here, right? So both of them are like about this high, right? But guess what? Now that they're in equilibrium, there's no more heat flow, right? No more heat flow. And so no more useful work can be done essentially. And so this is quite an interesting concept because you might still say that yeah, it has some energy, but really physically speaking, there is no energy left in this system, this kind of two block system where the temperature is the same. There's no more useful and there's no more energy between them because there's no ability for them to do work, right? Not without me introducing some additional energy from the environment. So yes, if I'm able to influence it from like surrounding environment, yes, some work could be done. But if I'm just like isolating these two blocks, like let's say their own universes, right? Then nothing useful can be done anymore. No work could be done anymore. And so we say really that like these two blocks have no energy, right? Because they can't do any work. And so this is what I mean by energy is very much a relative thing. So when we have this situation here where one block or one system is 20 degrees, the other one is 70 degrees, yes, there is energy between these two systems, right? Because there's some difference between them and you know relatively, and so because of that you know there's some ability for this block to do some work on this block, but once they're the same, there's now no ability for these two blocks to do any work. So we say that there's no energy between them, right? So you know this all of this is pretty much a very roundabout way of me trying to explain that energy is a relative quantity and it's important that it's relative quantity, right? Because yeah, if all the bodies of an isolated system are in the same state, i.e., yeah, again in equilibrium, right? Then nothing can happen, no work can be done, therefore no energy in the system. So this system here has no energy. Okay. And so what really then is energy is pretty much it's kind of like a mathematical tool, right? It's a way for us to um describe or mathematically describe, and it's an abstract accounting tool, right? So it's something that we use to quantify the capacity for a system to change or for an object to be in a different state, right? Or between two different physical condition, right? So again, it's yeah, it's just a number that we use to kind of describe that difference relative between two things, if that makes sense. If not, that's okay. But I just want to kind of to try to explain to you that yeah, energy is quite complicated. Or well, it's not complicated, but like conceptually, it's quite difficult to understand. Um, but we use it a lot because it's quite useful to measure these difference and then therefore go on to talk about like oh how can these systems then do work, like what useful work can be done from it. Okay. But if all of that went over your head, that's okay. Yeah, that's all right. That's not the most important one, but I think it's interesting. Do recommend you to go watch the YouTube video though. I think he explained it in probably a bit better detail than I did. But if you understood it, great. Okay, never mind. Let's keep moving on. Just wasting time. Okay. Next thing to talk about then is kinetic energy. Now this part is important that you need to know, right? So when you have an object in motion, that object has the ability to do work, right? As we discussed over here, right? So when you have a block here in motion, it's able to then cause the ball to go into motion because it can do work on the ball. So an object in motion has the ability to do work, and so we said that it has energy. Specifically, this type of energy is called kinetic energy. The reason why it's called kinetic energy is because of the ancient Greek. The word kinetikos means motion, and so that kind of stuck around, and now we have the term kinetic energy. Important to emphasize that when we talk about kinetic energy here, we are talking about the translational kinetic energy, which means XYZ, right? So moving up and down, side to side, backwards and forward. We're not looking at rotational, so not thinking about like how things spin. There is such thing as rotational kinetic energy, but again, you probably do it more in uni if you want to do physics in uni. So equation for kinetic energy, half mv squared. I think hopefully you have seen this before. If not, then well, learn it now. It's also in your formula sheet, I'm pretty sure. So EK, the kinetic energy, is equal to half times the mass times the velocity squared. Yeah, so we say that, yeah, kinetic energy is directly proportional to the mass, but it's proportional to the squared of the speed. And so if I double my mass, right, so if I go instead of m, I then instead have two m's, my kinetic energy will also double. Right, makes sense. Double the mass, so two times the mass. I double my kinetic energy. Fine. Uh, if I double my speed though, or double my velocity, right? Then because of the square, I actually end up have to do four times the kinetic energy because two squared is four. So if I double my velocity, I've actually increased my kinetic energy by four times. And so what does that mean? That means that an object that is that travels twice as fast has four times more ability to do work. Right? Yeah. Um, because of the connection between work and kinetic energy, the energy is measured in the same unit as work, which is in joules. Or rather, I'll probably say that work is measured in the same unit of energy. But yeah, so joule, capital J, right, is the unit we use to measure kinetic energy. Okay. Uh, Again, because energy is a relative quantity. Well, like when we look at energy, we care more about the relative energy between two objects. It usually makes more sense for us to look at change in kinetic energy rather than the absolute kinetic energy itself, because absolute kinetic energy itself means absolutely nothing, right? Because like yeah, like depending on my perspective frame of reference, I could change my speed to be whatever I want, right? Because yeah, again, if I move faster relative to the object, move slower, I change my speed, right? So the actual kinetic energy itself, then yeah, it's not important. It's the change that's important, right? Now you might ask, where does this equation come from, right? Where does the half mv squared come from? And so I will show you. Okay, so it pretty much comes from Newton's law and kinematics. So if you have here, right, I have here again my box, a box with mass m, with some initial condition. So it's initially traveling at some velocity vi. Okay, some initial velocity. I'm applying force to it though. So maybe let's say that I have a rocket here, a rocket launcher that's kind of, you know, causing it to speed up. So there's a force being applied to it, and because there's a force being applied to it, oh, I should say there's a net force being applied to it. So maybe there's friction, doesn't matter, right? I have some net force. So net force is not zero. That means acceleration is not zero. So the box is now speeding up, right? And because it's speeding up, that means that the velocity is changing, right? And so after a while, so let's say I have a constant force. After a while, the rocket ran out of fuel, so I ran out of the rocket. So now in final state, I have here the box traveling much faster at some final velocity. So this is my initial state, my final state. And in that time, it travels some displacement. And so at this point, it probably should now start getting some PTSD about kinematics, right? Because this is pretty much a kinematics equation. So do I have enough space here? Yeah, I have enough space here. That's fine. So let's have a look at the work done by the force on this object. So if you remember the equation for work is just the dot product between the force vector and the displacement vector. I probably should use D here because it's labeled as D here. And we know that we can simplify that to F D cos theta. Theta in this case is 0 because the force applied and displacement is parallel to each other. So theta is 0, therefore cos of theta becomes 1 because cos of 0 is 1. Okay, so my work here is just equal to force times displacement. Awesome. Okay, now the force, or the net force in this case, is just equal to mass times acceleration, or the net acceleration, which doesn't make sense. It's just acceleration, right? Because yeah, the object only has one acceleration. So the mass times acceleration, so that's F equals ma, and then I put the d here. So I see that work done is equal to ma d. Coolios. Okay, so from here, what I can actually do is I can tap into some of the kinematics principle, right? If you remember, I have one equation. Whoa, oh, that's cool. Okay, I have one equation, which was final velocity is equal to initial velocity squared plus 2a acceleration times s, or displacement. In this case, let's use d. You can probably see that I have here AD, and over here I also have AD. So what I can do is I can substitute this in. I should have probably gone to a different page, but whatever. So I can then see that the work W is equal to M times, if I rearrange it to make 80 the subject, then that's just literally Vf squared minus Vi squared divided by 2. Or if I want to kind of rearrange it a little bit, so I have half times M times Vf squared minus Vi squared. And so if I want to expand it even further, right, I have here half times mvf squared minus half times mvi squared, and that's equal to work. And if you remember to our discussion earlier, how work is the transfer of energy, right? So when I'm transferring energy, that means energy has changed from one quantity to another. So there's some final state, and you can subtract it from the initial state. And so people probably went like, hang on, right? I have some quantity here, right? Some final quantity here, right? So half mvf squared, and I have some initial quantity here. Let's call that kinetic energy, because when I do work on this block, it starts moving, right? And so because it starts moving, the kinetic energy has now changed. And so how does it change? Well, it changed because the velocity has changed. And so now I have my final state here. I have my initial state here. And so just from derivation over here, pretty much that's how we kind of spit out that kinetic energy is just equal to half mv squared, right? It's literally just from the derivation there. I'm not actually sure which one came first, but if my gut is correct, I think that like the kinetic energy formula is probably derived this way, but I'm not too sure. Okay, so don't quote me on that. But again, we don't really care about the absolute amount of kinetic energy itself, because velocity can change. And so really what we care about is actually this, right? The half times m times vf squared minus vi squared, or what we call the change in kinetic energy, right? And so from here, we now have a relation, right? We say that the work done on an object is essentially equal to the change in kinetic energy. But note that our work that we derive in this case, we actually use net force, right? So this work here really is net work, right? So this is net work. So this is a key principle that will come back again and again So please make sure you have this ingrained inside your head. The fact that net work or work total, the total work done by all forces, so all forces, and this is work net, right, is equal to the change in kinetic energy. Okay, so that's my work energy principle, right? Yep, so the net work on an object is equal to the change in the object's kinetic energy. Yeah. And so the work energy principle is only valid if work is the network, right? I can't just use any work. I can't just use some random forces. This relationship here, right? As we derived it, right? And I showed you how to derive it, so it probably makes sense. It should make sense that this only works for net work and not other work. So not work done by gravity, not work done by some random force. It's a combination of every single force, the total network that if it's a positive value, then there's a positive change in kinetic energy. If it's a negative value, then there is a negative change in kinetic energy, right? So I should probably note this down. So positive work net, that gives us a increase in kinetic energy, right? And if I have a negative net work, then that tells me that it's a decrease in kinetic energy, which makes sense, right? Because in order for network to be for the network to be negative, that means that like my net force have to be in opposite direction to my displacement, which means that it's slowing down. And if it's slowing down, that means that there's a decrease in energy. And then in the other way, if I have a positive network, that means the net force is in the same direction as my displacement, which means that I have now an increase in kinetic energy because it's going faster. Okay. Yeah, so we've derived this pretty much just using Newton's laws and some kinematics, right? So nothing super new. Yeah, anything else I have to talk about here? Great, okay, that's fine. So let's do some examples, right? I think examples is important to kind of help us sort of consolidate our understanding. I don't have space here, so let me magically add a page. There we go. Was that the right page? No, that was not the right page. Let me add a page here. There we go. I have a page here. Okay, so I have two examples here. I've got a hammer hitting the nail. This is not really a question. This is more of an explanation, right? So if you have a hammer hitting a nail, right, and then coming to rest, you know that the hammer exerts a force on the nail. And then because of Newton's third law, the nail also exerts an equal opposite force on the hammer, right? So these are force pairs. Again, remember, force pairs always happen on different objects. So this force here is on the nail, this force here is on the hammer. Great. The work done on the nail is positive, makes sense, right? Because the force on the nail is this way, the displacement of the nail is this way. Therefore, cos of theta in this case equals 0. Cos of 0 is equal to 1. That means that I have a positive work on the nail. So work net is positive for the nail. Okay. On the other hand, if you analyze the work on the hammer, work done on the hammer by the nail, we see that this is the force done on the hammer by the nail is going this way, but the displacement of the hammer is going this way, right? And so now I have my theta, the angle is actually 180. So cos of 180 is equals to -1. That means that the work done on the hammer by the nail is actually negative, right? And again, negative work, what does that mean? That means that is a decrease in kinetic energy, which makes sense, right? Because when I'm smashing the hammer, when it hits the nail, the hammer slows down to a stop. On the other hand, the nail was actually stationary, but then with the work being applied, it being positive, it actually speeds up into the piece of wood, right? And, again, with network, there's now transfer of energy, right? So hopefully we're all good there. Okay, some more mathematical question. Here we have, give it a try first before you listen to me do it. I'm conscious that I probably have been talking for a very long time, but that's okay because I'm on video now. And so you can play me at a one and a half times speed if you need to. That's not permission for you to do it, but you can. So with this question here, I have work on the car to increase the kinetic energy. So how much network is required to accelerate a 1,000 kilogram car from 20 to 30 meters per second? So then simple application, right? I can go, well, network is equal to change in kinetic energy. If I want to find my network, I just want to look at the change in kinetic energy. So in this case, half times m times vf squared minus vi squared. I just do it in a bracket. You can do just half vf squared minus half m vi squared. Same thing, right? But I think this one's a bit easier. So half times, oh, I'm probably blocking the way. Here you go. Half times the mass. Our mass of the car is 1,000 kilos. Velocity, make sure unit is in SI unit. So kilogram, that's fine. Meters per second, that's fine. Meters per second, that's fine. So final velocity, 30 squared minus initial 20 squared. So that should give me, let me put into my calculator. Half times 1,000 times 30 squared minus 20 squared gives me 250 kilojoules to 50 kilojoules, or 250,000 joules. Okay. That's pretty much it. I think that's right. That's right. Yep. Pretty sure that's right. Okay. There you go. If I'm wrong, put it in the comment. Actually, you can't, because this is an education video, so comments are disabled. Email me. Cool. I actually need this page. Let me just delete that. All right, next one. Again, please do give this problem a try before you watch me do it. So I've got two cars here. Pause the video. Do it now. A car traveling at 60 kilometers per hour can brake to a stop in a distance d of 20 meters. If the car is going twice as fast, what is the stopping distance, assuming the maximum braking force is approximately independent of speed? So what does that question actually mean? That question just means that, force is constant. I've doubled my speed. So what's going to happen to my stopping distance? Well, if you remember back when we talked about kinetic energy, right? So we say that Ke is equal to half mv squared, or if you want to use Ek, up to you. In this case, I have now doubled my speed, right? So if I've doubled my speed, so v, that's not a v, v becomes 2v, that means that Ke has to become, again, right, 2 squared becomes 4 times kinetic energy. And if I have 4 times change in kinetic energy, that would mean that, remember with our work energy relation, work network is equal to change in kinetic energy. If I have the change in kinetic energy is 4 times, 4 times change in kinetic energy, that would mean that I have 4 times the net work. If I have 4 times the net work, remember that work is also equal to force times displacement, right? With these questions, it says that the braking force is approximately independent of speed, so the force is constant, so that cannot change, right? So that's locked in. And so if I have the force as constant, but then the work is 4 times, that means that the stopping distance also has to be 4 times larger. So instead of stopping in 20 meters, I just have to go, my stopping distance is now 4 times 20, or 20 times 4, which is 80 meters. Okay. And I do want you to try to see if you can. Would you be able to calculate this one actually? Yes, I think you should be able to calculate this one because the masses should kind of cancel out, I think. Probably. Give it a try. See if you can actually mathematically calculate it. But for this one, I've just done it by ratio. Just I think it makes our life easier rather than, working out what the acceleration is going to be. In order to do that, you have to convert your kilometers per hour to meters per second for both of them, right? Work out the acceleration. Then with the acceleration, you can work out the what are you working out? The force. Yeah, you can work out the force, and then with you have the thing for kinetic energy, but then the mass kind of cancels out, so you have to go what is it? F times displacement is equal to half mvf squared minus vi squared, and then you have to go, well, mas, right? F equals ma is equal to half mvf squared minus vi squared. The m's cancel out. Um, you have to work out the acceleration, just again using kinematics, and then from there you should be able to work out the stopping distance. So give this method a try. See if you can actually arrive at the same conclusion of 80 meters. But I still feel like logically working it through using work energy relation is a bit easier. But that's up to you. Okay. Is that the last question? No, that's not the last question. I now have this one. What's this? What do I have to talk about? Oh, because it's stopping. Also, sorry, got to say, because it's a stopping thing, right? Remember that F dot S will have to be negative, right? Because force is braking force is going this way, displacement is going this way. So now I have an angle of 180 degrees. That means cos of 180 is equal to -1. So I actually have a negative work here, which then should cancel out with this. Yeah, should cancel out with this. Yeah, yeah. So give it a go. See if you can actually solve it. Cool. Last question I want to look at. Phil pushes the textbook from rest across the desk towards Ranji, applying a constant force of 60 newtons for a distance of 5 centimeters. At the same time, the book is subject to friction force of 10 newtons. Calculate the change in kinetic energy of the book. Again, could just work out the kinetic energy. I think it's a bit hard, or like not hard, but a lot more tedious, a lot more work. Get it? A lot more work. But if I just go by looking at work, I think that's actually not too bad, because if I always draw a diagram, right? If I draw out my textbook, I know that I have a force being applied of 60 newtons. I know that there's a friction force of 10 newtons in the opposite way. This thing has traveled a distance of 5 centimeters. If I want the change in kinetic energy, right, I just have to work out the network. Network comes from net force, right? So my net force is, in this case, 60 newtons minus 10 newtons, because this side is positive, this side is negative, and that equals 50 newtons. I have my net force. I just have to go, well, net force times the displacement x is equal to, in this case, 50 times 5 centimeters is 0.05 meters. Right, put that into my calculator. 50 times 0.05 gives me 2.5 joules. So the change in kinetic energy in this case is 2.5 joules, because we know that net work is equal to change in kinetic energy. Again, Note that I'm not looking at the work of this applied force, or not the work of the friction, or not even the work of the normal force and the force of gravity, right? I didn't even need to look at the force of gravity and friction force for this case. I just had to work out the net force times by displacement. That tells me the change in kinetic energy. And then from there, I can calculate the final speed of the book, right? So this is from rest. So I know that my change in kinetic energy, let's do it down here. Change in kinetic, ew, that's not a K. Change in, kinetic energy is equal to 2.5 joules. That's equal to half mvf squared minus vi squared, and that's equal to 2.5. I know the mass of my book is. Do I know the mass of my book? I do not know the mass of my book. Hmm. That's interesting. If I don't know the mass of my book, how am I going to do that? Textbook across the from rest across the range, applying constant force of 60 newtons for a distance of 5 centimeters. At the same time, the book is subject to friction force of 10 newtons. Calculate the final speed of the book. Hmm. Are we missing information? I feel like we might be missing information. Unless it's the same. Did I just wait? Give me a second. Let me check the textbook because I feel like we're missing information here. Play elevator music in the background. Where's my phone? Oh no, I'm using my phone to record. Bummer. Okay. Well, that's unfortunate, ain't it? I can't log into the textbook. Okay, you know what? I'll pause the video and I'll get back. Okay, yep. So apparently the mass of the textbook is 1.5 kilos. Just wasn't there. Yep, okay. So the mass of 1.5 kilograms. So then once you have that, you can pretty much just solve it, right? So half times the mass 1.5 times my final velocity is what I'm looking for, minus 0 is equal to 2.5. Just algebra now, right? So VF squared is equal to 2 times 2.5 divided by 1.5, and then therefore VF is equal to square root of that. And that should give me, what does that give me? 2 times 2.5 divided by 1.5, 1.8. Approximately 1.8. Approximately 1, oh geez, okay. Approximately 1.8 meters per second. Okay, so hopefully that's somewhat clear. And look, if you need any additional help, please do feel free to email. Yeah, and other than that, I think that's pretty much all I have to say about kinetic energy. Next one to talk about potential energy. Cool. Very good. All right. Goodbye. See you later.